My name is Qianxiao Li. I'm a scientist at IHPC in A-Star. I work primarily in applied mathematics, so I'm interested in the theory and algorithms for machine learning. At the same time, I'm also interested in applications of machine learning. So that's why I work with many colleagues in IMRI IHPC on various applications of machine learning, some very modern machine learning sometimes, for process optimization, characterization, discovery. So today I'm going to talk about a very sort of simple and hopefully accessible introduction to some basic applications of machine learning methods to material science. So the first challenge, or scientific challenge I want to address is the following. It's called property prediction. So suppose you have some material composition, or more generally, this can also include some processing conditions. And this sort of thing, you can think of it as things you can control in the lab or in your simulator. Okay, so you can choose what kind of materials you're going to use and what kind of conditions you're going to use to process the materials. And eventually, they will give rise to some material properties. For example, strength, elastic moduli, etc. And presumably, there is a relationship between the two, right? And your goal of doing the experiment in the first place very often is to find out what the relationship is. Our question is, if given enough pairs of data, can we discover this relationship from data, from the data's driven point of view? Okay, so this is the very first question. And the next question kind of follows on from this one. After discovering this relationship, the question is, what can we do with it? So very often you do experiments precisely because you want to optimize certain outputs of this experiment. For example, you have some material property, say strength, and you want to maximize the strength. But at the same time, you also have some, let's back up. At the same time, you also have some material constraints. For example, some components might be very expensive, and you want to minimize the amount of particular component you use. And of course, there's a lot more complicated constraints that you can have. So given these constraints and desired properties, the question you can ask is, what can we do in an experiment in order to achieve these desired properties and compositional constraints? So from this point of view, data-driven approaches using AI and machine learning can also help guide the optimal composition or optimal processing conditions that you need to have in order to achieve these goals. So the question we want to ask and answer today, hopefully, is can we use data to complete this process? Okay, so you can think of this as a cyclical process. So why is this difficult without using the computers to aid us? So here's a data set that we're going to play around with a little bit today. So each of this row, you can see there's about 1,000 rows. These are truncated, represents a particular experimental data point. Okay, and each of this column the first few columns represent the inputs or the composition and processing conditions, and the last column is the output or the material property. So you can see that there's many dimensions, both in this way and this way. So if imagine that you want to use a traditional inference method, let's say you want to plot some relationship on the graph, on a piece of paper, you'll find it's very difficult to visualize and characterize this relationship. So you really need some more sophisticated data-driven tools in order to extract some underlying patterns from this sort of setup. Okay, we're going to first focus on the problem of property prediction. And it turns out that the property prediction problem can be formulated very naturally as a supervised learning problem. So now I'm going to explain what I mean when I say supervised learning. So suppose we have some composition, we'll call it big X, and we have some corresponding property. So again, this composition is something that you can control in an experiment or the simulation, and Y is the result of the experiment or the simulation. And we know that there must be some relationship between the two. So Y is a function of X. But the problem is we don't know what F is. Okay, at least partially most of the time, we don't know what F is. So the question is, can we learn F from the data, right? So what is the first step? The first step is you have to collect some data. So here, xi, yi are data points. So that sort of basically says these are the experiments you have already done with the input x and the output y. And you collect them, and because we know this relationship, we know that yi is a function of xi with some noise, but we don't know this f. Okay? there's some noise because often when you do experiments, there's going to be uncertainty, both systematic and random ones, right? So we allow for that. And the next part is we form a model. Okay, so what does forming a model mean is you're going to form a search space of all possible models, hopefully a small subset. And you want to find the best model that approximates the relationship that you have seen from the data. So here, f hat is kind of a model for f. And this theta is a set of trainable parameters that you can adjust. And when I say training or learning, it's basically adjusting this parameter so that this f hat approximates f. Okay? So we do this by minimizing some loss function between the actual outputs you have seen in your previous experiments and the predicted outputs you have seen based on your model. Right? And you optimize your model to minimize the difference. If this sounds a little complicated to you, let's give an example. So linear regression is perhaps the simplest example of doing this. Okay? So in linear regression, your f hat, your model space, is the space of linear functions. So you say, I believe there's a linear relationship between x and y, right? But I don't know what the coefficients are. And these coefficients are theta. And you want to minimize the squared error between the prediction and the actual targets by adjusting the slope and the intercept. So this is basically this process, okay? But today we're going to introduce models that are slightly more complicated than linear regression. Okay, so without further ado, I think it's useful to just get our hands on this actual problem of a problem of predicting the concrete compressive strength based on its components. So we all know that concrete is composed of many different ingredients like cement, fly ash, and blast furnace, and et cetera. So these have to be mixed in the right proportions in order to give the right kind of materials that you use to build things, right? So in this case, all these, you can think of it as x, and certain properties of the concrete is y. And the first step is we collect a bunch of data set. So here we're going to use an experimental data set that's openly available online that links this relationship. So in the first few columns here, 8 columns, I believe, these are the inputs or the material composition and processing conditions. Okay, so these are the composition, and this is the H. And the last column is the target. So this is, we measure the strength, like the concrete compressive strength in megapascals. Okay, so the goal is, can we find out from this whole data set the relationship between the input X and output Y? Okay, so we have mentioned that linear regression is perhaps the easiest model that you can have. So maybe we should try that first. So let's start this demonstration. So you're going to click Start if you're Windows and type Anaconda. So we want to launch the Anaconda Navigator. So click that. Okay, well, while we're waiting for it to open, you can see that there's a lot of variations. Oh, you can see. So for each of these columns, right, there's a lot of variations between different inputs, or sometimes I call it features. So you would expect that, given this sort of variations, it's very unlikely there's a linear relationship. But nevertheless, a linear baseline is always useful when you do data analysis to make sure that when you're using a complicated method, you're actually gaining something. Okay, so this is why you usually start with the simplest possible method to get a baseline of how well your algorithm actually is. Okay, so if we go to the Anaconda Navigator, and very importantly, we have to change the environment to the one that we actually install the right packages to. So you want to click here and navigate to the workshop environment. Okay. And then once you are in the workshop environment, launch Jupyter Notebook. So this is the icon here. Just press Launch. Okay, so this will actually launch a browser. So this will display a Jupyter Notebook here, as you can see in your browser. Okay, so let's navigate to the the workshop folder that you should have downloaded or cloned from GitHub. By the way, if you have trouble following, just ask around your neighbors. Okay. And then we are going to do the probability prediction folder, so click on that. And you should see there's this demo.ipynb. This is the IPython notebook that we're going to use for the demo. So click on it, and it will load. Okay, so while we wait a little bit, let me just give a quick introduction to what Jupyter Notebook is. So those of you who have used Mathematica will find this very familiar. So this is kind of a Python programming environment, except that it's interactive. So you can run every cell individually and check the results and plot the graphs. And you can also write notes about your research. So it's much easier to share it and disseminate it. Okay? So the basic usage is every cell can be run individually. So when I say run a cell, for example, so these are the nodes cells. So you can see these cells are just nodes. Okay? That's written in Markdown. And this kind of cells with the bracket here, this is the code. All right, so you can run this code. And the way to run this code is you can click on the cell, or you can use the arrow keys to navigate to the cell, and then you press Shift and Enter. Okay, so that will run the cell and go to the next cell. Okay, so we're going to repeatedly use that. That's all you need to do to run the code. Okay, so what is this doing? So this is first going to import some libraries. You can see NumPy, Pandas, etc. So these will help us import the data sets and manipulate it. Okay? Okay, so the very first step we want to do is to actually load the data set, right? So this data set is actually downloaded in the Excel format. And the way we can load the data set is by calling this pandas function called pd.readXL. So this is a can function that helps you input your Excel data set, read it, and convert it into a data frame, a pandas data frame. So what does that mean? So we go to this cell, click it, or press down arrow to navigate to this cell, and press Shift Enter. Okay, so this will read the notebook. Read the Excel file into the notebook and display the data frame. So you can see df is actually, you can think of it as an array, but it has all the headers in the right place. So it looks a little bit like your Excel file, okay? You can see it tells you that there are about more than 1,000 rows. So these are experimental conditions. And so each row is experimental data point. And you can see the first 8 columns, these are the inputs again, and the last one, the compressive strength in megapascals, this is your output. And you are trying to, and what we are trying to do is to quantitatively discover some relationship between the two. Okay? So before we actually do the model, I need to talk about something that's very important in machine learning, in that how can you evaluate how good your model is, right? So why is it that you shouldn't use the whole training set to do your training? Okay, so here is what I propose. Suppose we have more than 1,000 data points, and I'm going to make a model that remembers every single data point and give you the right output, okay? You're never going to do better than my model on this data set because my error is 0, okay? I get everything correct. But it's not hard to believe that that's probably a bad way of doing things, okay? So how do you evaluate the model is that you need to keep an independent set that the training has never touched. So when you're training it, you should not look at some of the data sets that's used for evaluation, okay? So in this case, if you just memorize the training set, this is not the complete set, and you're going to do very poorly on the other set. So this is why we do such thing as train test split. So this just means that we're going to, out of this 1,000 samples, I'm going to keep about 800 of them and use it for training. And I'm going to leave the rest of them for evaluating the model. The most important thing here is that during training at any point, you should not look at the test set. Okay? After training your model, after making your model, only during the evaluation should you look at the test set. All right? That's the point of having the test set. Okay. So to do this in Python is very simple. So we just call the function train test split. So here the test size is 0.2. That means I keep 20% of all the training data as test data. Okay, the rest as actual training data we're going to train the models on. So press Shift Enter. So that will split the data set accordingly. And now we're going to do a linear regression, right? It's a very, very exciting model. So as I alluded to earlier, linear regression is nothing but a hypothesis that your output is linearly correlated with the input. Okay, this might not be right, but let's just do that and see what happens. Okay, so in this case, there's only about 5 lines of code, but you will see repeatedly that this is often all you need to do if you use the sklearn library. So the first step is we want to import the linear regression module. Okay, and then the second line here, we instance a class of this regressor. So this is a linear regressor, and we're going to fit it on our training data. So importantly, again, the third step, we fit on the training data. We didn't touch the test data. So after fitting the model, we're going to use the fitted model regressor here, and we're going to predict based on the training set, and we're going to predict based on test set. Okay, and then we're going to match these predictions with the actual values that we have, because remember, we have the whole data set. Okay? So to run this, just press Shift, Enter. All right, and that's done. And we can plot the predictions. So here I put all the plotting commands into the Python script. You can check out what it is. So press Shift, Enter. And we can see this graph pop up. Okay, hopefully you're close to this step. Okay, so there's 2 graphs. On the left, this is based on the training set. So this is a set we have seen during the fitting the model. And on the right is a test set that we have never seen. Okay, on the horizontal axis, this is the target compressive strength. So this is actually the true experimental measurements of these data sets. Okay, and the vertical axis is our predictions based on our linear model. So let's say if we believe that the linear model is the right one, then this is the model, this is the best prediction we can make. And of course, if your predictions are all perfect, then all of it should be on this line, x equals to y, right? And obviously, you can see that this is not perfect, not close. And the way we measure the error is by this measure called RMSE, which stands for root mean square error. So there's one way to measure the errors. So the root mean square error is just the square root of this value that we introduced before, this one, which is your objective function value. So the objective function is already a mean square error. So we just take the square root, and that will give you the right units. So the units of the root mean square error is also megapascals. Okay. So a few important features. Number 1, you can see that the spread is quite big. So your model is not so good. But interestingly, you can also see that on the training set and the test set, the performance is similar. Okay? So this is what you often see when you use a simple low complexity model. Okay? What is another example that's low complexity that is guaranteed to have this sort of similar performance on training and test set? For example, I can randomly guess. Okay? So instead of fitting anything, I don't care what the input is. I'm just going to randomly guess a number between 1 and 0 and 100. So you can see, that model has no complexity whatsoever. I don't need to train anything, right? But on the test set, on a training set, you're probably going to perform the same. Okay? Later, we will see instances where models become highly complex, and you can see there's a big difference between the training and the test set errors. Okay? And that will lead to important issues called overfitting, which we'll cover later. Okay, so let's go back to the presentation. Okay, so there is some questions saying that what class is used. Yeah, so you can check out the code by seeing what kind of imports. Sorry, the question is the question was what kind of new functions did we write that was not standard part of this this library, if I understand this correctly, sklearn library. So for me, for this presentation, the only functions I wrote is on the plotting functions, which is just thin wrappers. Okay. Sure. I think yeah, we'll do that. Yeah. Okay. Okay. So let's go back to the discussion. So now, just to remind you, we did a linear regression, right? And we saw some interesting features. Now, of course, we want to do a little bit more than linear regression. You can see that the error is not so good. So today I'm going to introduce to you something of a different kind of regressor that's more, potentially more robust for fitting nonlinear models. Okay, it's called decision tree regression. And So the main idea of decision tree regression is to make certain splits or decisions in your feature space. So without explaining that, I would just refer to the picture. It's much easier to see. So here in this picture, I'm trying to fit a sine function. So, So these data points are, an xi, yi values that you collect. Okay, so this you can think of it as your experiment, and it follows some sine curve. And we're trying to fit this. Obviously, if you use a linear regression, you're not going to get a perfect fit no matter what you do, right? So this is not a linear function. So what decision tree regression does is the following. First, if we just look at this, this orange one, the max step equals to 1. I'll explain what that means. So what we're going to do is the following. We're going to make a decision here on this x space to split the data into 2 parts. Okay? So we split at 0. And to the left, we're going to assign just one value. Okay? It's always going to be this about 0.8 or something. And on the right, I'm going to assign a different value. Okay? So that's all there is to it. That is my decision tree regressor. Okay? I make a decision on where to split the thing, and then I make a decision of just assigning a constant value. So this is called a piecewise constant approximation. Okay? They're always flat. Now, of course, this is probably not a very good regressor. All right? So what I can do is I can recurse this. So once I'm on this side, I can say, okay, I'm going to make another split. So this is the depth 2 tree here. And I'm going to assign one value to here and one value to the middle portion. And I do the same on the right-hand side. So you can see this curve is a slightly better fit, okay, to the sine curve than the original one. All right. So if you do that, this is pretty overview, a cartoonish kind of routine, how decision tree regression is being trained. Okay, so this is pretty much what it is. And you can see that there's some advantages in that it can gradually, if you tune the number of decisions properly, you'll be able to map out this function to a satisfactory degree. Whereas you could not do that using a linear model. Okay, so this is very simple. So the advantage, besides being able to fit nonlinear functions, is they can handle both categorical and numerical inputs, and also can handle classification problems. If you don't know what those mean, you just read up more a little bit more on the decision tree regression. So I'll provide the references later on. But there's a disadvantage. So you can see that when the depth is low, it means the number of splits you make is low. Your regressor is probably not very good, like for example this one. Okay. But if you make too many of these decisions, it's not hard to imagine that you're going to run into some problems. So later on, I will talk about, I will actually illustrate to you numerically what problems you may run into. But let's talk about one way to improve this. So we want to, make decision trees simple, but at the same time, we also want the error to be low. So what we can do is the following. So I'm going to introduce to you a method of ensembling. So what does ensembling mean? Model ensembling, as the name suggests, is to take many models and put it into one model, right? That's what ensembling means. And in particular, it basically says we want to combine a bunch of weak models, weak learners, which kind of like low complexity models, into a strong learner of high complexity. So how can I do that? Boosting, and in particular gradient boosting, is one efficient way of doing that. So here I'm going to give you a very kind of high-level introduction of this idea of boosting. So suppose we have some weak learner. Okay, so in this case, it's this one-step function. So the question is, how can we improve this? Okay. So one thing we can do is we can take this function. This is the target, and this is our current regressor, not very good, and we take the difference. So we take the difference. This is called the residual. If our function is perfectly fit, of course the residual will be 0, right? But this is non-zero. Okay. So what do? Naturally, we fit another decision tree to this residual. Okay. So after fitting this decision tree to the residual, okay, this is sort of a mathematical formula, and I'm going to add it back to the original tree to form this new estimator. And you can see that I've improved it a little bit, especially on the left-hand side. All right. So overall, this is what boosting means. You compute the residuals, and you fit the residuals using decision tree methods, for example, in this case. But of course, gradient boosting itself is a lot more complicated, and I encourage you to read about what's the best way to pick this model space where we fit the residuals, as well as how we can add the residuals back. So there's more nuanced ways to do that. But the basic idea is basically this. Okay? The advantage of this is that gradient boosting with decision trees is very robust. You can handle a variety of problems, classification, regression, with very low, it doesn't even need many samples to have a very good estimation. Okay? And at the same time, it can also give you some measure of feature importance. So I'll not go into details of how that is done, except that if you think about this, when you do decision trees, you're making sort of splits in the data, and then you approximate it with some constant function. Every time you do this kind of split and approximation, you decrease the loss function. So you can ask, which split in which input did I decrease the loss function the most? So that is the most important feature. So this gives you a measure of importance of how your inputs affect your outputs. Okay, so this can be used in some feature selection problems. Okay, so let's now demonstrate how gradient boosting can help our original regression problem compared to linear regression. So let's go to the demo. Okay, so this is where we are in section 2. Okay, so the way we do this, if you compare this piece of code with the one with linear regression, you can observe that the only thing that changed is these words. Okay, so instead of importing the linear regression module, we just import the gradient boosting module. Of course, there's more options here, so we'll talk about that later. But let's just fit just a canned gradient boosting regressor. So fit this by pressing Shift Enter. Okay, so that's done. Let's plot the results. All right, you should see something like this. And you can see, well, compared to the linear regression problem, which is the root mean square error is about 10, this has improved it by quite a bit, right? Both in the training set and the test set. At the same time, you can see that there is now a significant difference between the training set and the test set errors. Okay, so this is usually expected when you have a model with enough complexity. Okay, at the same time, you can also look at feature importance. As I said, how important is one particular class of input in affecting the output. So if you press Shift Enter, this will give you a measure of that. So on the horizontal axis is kind of a normalized measure of how important your feature is. So the bigger the number, the more important it is. And the vertical axis is all your different compositions and processing conditions. Okay, so you can see, age is very important, whereas the fly ash component seems to be less important in this particular model. Okay, so it can help you do some feature selection. Okay. Okay, so we have shown that gradient boosting has some advantages, but is it always better than linear regression is the problem? Or is it always good? Now, it turns out that there is an important idea of model generalization and overfitting that you have to take note of when you fit a machine learning model to your data set. Okay. So in short, when we say a model generalizes, right, if the model trained on the training set also performs well on the test set, okay, and they're not too far apart, this is when the model generalizes. Okay. And the same should apply for any other unseen data from the same distribution. And if your model doesn't do that, then we say it overfits. Okay, so overfitting is when a model performs very well on the training set, but the better it performs on the training set, you observe that it actually performs very poorly on test set, which you have not seen during the training. Okay, so when does this happen? This can happen when your data set is too small, or your model complexity is too high. Okay, and the third one is you're not using the right optimization algorithms, and this is more of a recent discovery in the machine learning community. But the first two is well understood. And if you look at the plot on the right, I just give a demonstration of that. So we have the same problem of fitting this sine curve, except now that I add some noise to some of the data points. Okay, some of the data points are noisy. Now, if you fit a low complexity model, the max depth equals to 2, you can see that, oh, well, the fitting is not too bad. And in particular, it seems that if I give you a new data set, the performance should be similar. Whereas if I fit too complex a model, so in this case, depth equals to 5, you can see that many of these those spikes are trying to fit the noise, right? So this is, instead of fitting the underlying average value, you are fitting a noisy observation of the value. So you can easily imagine that if I redo the experiment, I'm going to have different noise patterns. The estimation by our model is going to be very bad. Okay, so this is usually what we call overfitting. So to demonstrate that, we can go back to our notebook. And let's do something bad to the gradient boosting regressor. So as we saw before, if your depth is too high, your decision tree depth is too high, you tend to overfit. So let's just do that. So here, I just changed the max depth from the default value, which I believe is 2 or 3, to 10. Okay? So let's press that, Shift Enter. Oh, sorry. I have to exit this. Okay, so if you go to, if you go to the demo, this 2.1 overfitting, and we run this cell. So you see that I'm going to adjust max depth to 10 instead of default value. And let's plot the predictions. Okay. Now you see on the training set, your model is near perfect other than a few outliers. Okay. This is basically, you can think of this as kind of memorizing the training set. Right? But on the test set, the error is actually a little bit bigger than before. Okay. Before that, it was 5.7 or 8.7 or something. So now your error actually increased a little bit, or at least it didn't decrease. So there's a huge difference between these two. So this is a sign of overfitting. So what can we do to correct the problem? So this is usually where the idea of hyperparameter optimization comes in, or hyperparameter tuning. So hyperparameters are what you call meta parameters of the fitting model. For example, the depth of the decision tree is a hyperparameter. Why do we call it hyperparameter? It's because it is not the parameter that you actually fit the model. So you don't train these parameters based on your training set. These are things that you sort of set beforehand to determine your model search space. Right? Once you define that, then you train the model by adjusting the training parameters. Okay, so here the example, the depth of the decision tree is one such hyperparameter. So how do we how do we choose the hyperparameters? Obviously, we don't want it, the depth to be 10. So how do we do this properly? So one way to do this in a very effective way is by cross-validation tuning. Okay, so what this means is that I'm going to repeat the following process. You give me a hyperparameter choice. For example, depth equals to 5. Okay, just give me that. I'm going to do something to my training set. So I take my full training set, okay? I'm going to split it into a few portions. In this case, when it's doing threefold, I'm going to split it into 3. 2/3 of the training set, I'm going to use it to fit the model. Okay, so I'll allow our model to see 2/3 of the training set. And for 1/3 of the training set, I'm going to test and evaluate my model on. So this validation set plays the role of the test set that we had before. Okay? And now I'm going to cycle through this choice through the entire training set. So I have 3 different choices. I average the scores. Remember, the score is how well you did on the validation set. And then this will give me an average score for this hyperparameter choice. Right? And then I can go on to choose another one, either randomly or with a list of hyperparameters you decide beforehand. And then I pick the hyperparameter choice with the highest score. Okay, so this is cross-validation tuning. Now, a very important question is, why can't you just use the test set? Right? We have already had a split of training set and test set, so why don't I just take a hyperparameter, train it on my training set, look at my test set, see how well I did. I pick the hyperparameter that did the best on the test set. What's wrong with that? Well, remember that our test set is to evaluate our final trained model. And the important thing you want to do is that your trained model should not depend on the test set. So you should imagine that you cannot see the test set. For example, the test set is with me and not with you. And you have to submit your model fully trained, and then I evaluate that test set. So if you do this tuning using your test set, your hyperparameter of choice actually depends on your test set. So you are actually fitting your model to do well on the test set. Okay, so that means that if I give you a new test set that you've never seen before, you might not do the best. Okay, so this is why it's not fair for you to peek into the test set to tune your hyperparameters. And this is why you need to use cross-validation. Okay, so let us demonstrate this and see if we can improve our model. So remember that, just naive choices of some hyperparameters might cause you to overfit. So let's do hyperparameter tuning. So here, this command prints out the documentation for this gradient boosting regressor. You can do this for any Python function, okay? And if you print it out, you can see this basically tells you what you should, what parameters this can take. And if you scroll down, you can see there are many different parameters, okay? So if it's the first time doing tuning, you'll be like, okay, this is too much. There's no way I can run through all of them. So what we do here is we're going to do some random search cross-validation. So this is exactly the process that we discovered, we discussed in the slides, except that now for each choice of hyperparameters, we're going to randomly pick it from some distribution I specify, instead of searching through every single possible value. So here I will use some statistics functions from SciPy, which is a scientific computing library for Python. So I'm going to define, just 4 hyperparameters I'm going to tune, and each of this will be, the first 3 will be random uniform integers, and the last one will be learning rate will be randomly picked from this list. Okay, you can read up about what each of these terms mean, but you can see that max depth is one of them that we search through, and we're going to search between 2 and 6. And so run this by Shift Enter. And now we fit a CV tune regressor. So fitting a CV regressor, cross-validation tune regressor, is basically doing the exact, so let's just run it, Shift Enter. So what this is doing is exactly what we introduced in the slides. It's going to make a 3-fold split of your training set, and then it will evaluate it on the validation set, and then repeat. And now we have 50 repeats of 3-folds, so we're going to do a total 150 fits, okay? And then this will take maybe about a minute. So very importantly, for the regressor CV, you can see that, again, we only fed the training set into it. Okay, we didn't feed the test set into it. Okay? Okay, so I think yours should be done by now. Okay, so if you can see the output, they actually output these 4 hyperparameters with the best numbers they have found using this sort of very short tuning. But let's plot the predictions based on these. So Shift Enter. Right? And now you can see after tuning with cross-validation, okay, we only look at the test set now, the root mean square error is about 4.7, which is better than what you had before, which is 5.7 or 5.8-ish. And again, the right side never entered part of our training algorithm. It was only used for evaluation. Okay. And at the same time, you can also look at how the feature importance change. Right. So this is the same explanation as before, but you can see there's some slight variations. Okay. So before going on to the next one, I will just quickly mention that although we just introduced, actually we only introduced one particular algorithm, but there are many different modern machine learning algorithms you can use for regression and classification. So for example, random forest is another way of ensembling that doesn't depend on boosting, but it's kind of a bootstrap method where you split the data sets kind of in a parallel fashion and train different models and averaging them together. And of course, there's also spot vector machines, kernel-based methods, nearest neighbors, and of course neural networks, which will be introduced later on by Xiaonan. And if you're interested in any of this algorithmic and even theoretical analysis of these machine learning algorithms, I highly suggest you read this book, which is quite a good introduction to general machine learning. Okay, so before going on to the inverse design, let me just take a look at some of these questions. Am I still using gradient boosting when I'm doing cross-validation? Yeah, that's right. So the cross-validation, you can think of it as a wrapper around any existing regressors. It can be gradient boosting. You can do it for linear regression, although there's absolutely nothing to tune for linear regression. But so you just basically, in the whole cross-validation process, if you look at here, I made no mention to what regressor I'm using. So basically, it's just training using different splits, okay, and averaging the scores. So you can use this for your neural networks, for example, and that's what people do, okay? Okay, so another question says, why not just do a decision tree with many splits instead of this ensembling method? So we can see actually in this plot that, oops, sorry. Yeah, in this plot, this is actually a decision tree with, with many splits, and it tends to fit the noise. So the beauty of this both random forest and boosting algorithms is that it sort of prevents that from happening due to the stochastic way that you combine these trees. So even one of them is overfitting some notion of noise. As you average over many trees, these things disappear. Many decision trees, these such things disappear. Okay, so if you're interested, please read up more about this aggregating methods. They're very fascinating. Okay, so the second part, which is pretty short, is on inverse design. So the question is, okay, now we know how to fit a model. It performs pretty well. And the question is, what can we do with it, right? So we have the model, which is f hat, and theta star means that we have trained our model, and this theta star is the best one we found. This should be a adequate representation of what's really happening in the lab, at least to some approximation. And once we have that, can we use it for some design? What does that mean? So suppose that we want to actually minimize or maximize some objective function. Say I want to make a concrete that has a certain strength or weight. And it has some constraints too, cost constraints, particular components, I don't want them. So this actually can be formulated as a constraint optimization problem. So here there are two terms. The objective function is the thing you're trying to optimize, and the constraint function can be written as the algebraic inequality, tells you that this has to be satisfied. You only want solutions that this is satisfied. Okay, so this is a constraint optimization problem. So for our problem of concrete, we can pose something like this, which is admittedly a little bit arbitrary, but we'll see how our model does. So maybe I want to minimize certain components. For example, the blast furnace slag and plasticizer and fly ash, and I don't want too much of it. But at the same time, I need to use this concrete for something. So I need its strength to be upper 10% of whatever I've seen, top 10%. And I don't want to put too much water, and I don't want to wait too long. So this age is like smaller than or equal to 30 days. So these are a bunch of objective and constraints. And the question is, can you tell me how do I make this, right? That satisfies these constraints and minimize this objective. So this is actually a very practical problem. How much I'm going to add for each of one of them in order to make this. And without any of this machine learning, you probably guess a composition, right? You look at the data set and say, I'm going to try this first and try that next. And that might be time consuming. But now we have a fitted model. So you can think of that model as your kind of a virtual experiment that does experiments very quickly for you, okay? So how can we do this? So remember that in essence, we have framed this design problem as an optimization problem, right? So we can use this kind of global heuristic optimizers. So global means I want to find the globally best, design, and heuristic means that I have no real way of telling me that I found the global one. So this is just a heuristic algorithm, but very often it works pretty well. And one particular algorithm we're going to introduce is a particle swarm optimization algorithm. So here is the equation, but you don't have to look at the details. I'll just explain to you. So X is the position. So what is the position? This is basically a design. Okay, you're trying to move this design around the design space, and hopefully you want to hit something that minimizes the objective and respects the constraints. So you want to move X, and we move X by giving it some velocity V. And this velocity is updated according to this rule, where we try to make the particle, right, the design, go to the best one it has seen so far, weighted with the best one globally. So they talk to each other and say, hey, I've discovered somewhere good. You should come here. But if someone else discovers something better, you will tell everybody that, OK, this is better. So animation shows you precisely this. So in the beginning, you know, all the particles randomly distributed, and now they found the little cluster, so it's getting people to come here. But here they're trying to get people to go there, and eventually, you know, together they will discover a very nice solution. And this is, in a nutshell, what particle swarm optimization is. Okay. Of course, this is just one particular algorithm. There's a lot of other algorithms, such as differential evolution, genetic algorithm, et cetera, et cetera. So I produced some references here that you can check out. Right, so now let's do this optimization. Remember, we have these kind of arbitrary looking constraints, and we really want to see how we can make this material. Okay. Okay, so let's just go to the notebook on inverse design. Now, the first step is, of course, we need the forward model, right? The f hat. Right, so now we've already tuned it. We just need to fit the regressor on the full data set. So let's do that. Okay, so this is basically taking, basically taking all the best parameters we found before, and then we're going to do a fit on the entire data set. Now, this regressor object will be our kind of experimentalist. You know, this is the thing that does experiments for us. And now we're going to do the optimization. So first we have to define some objectives. So some objective here, we want to minimize these compositions, and we want to respect these constraints. Okay. So here, this two Python functions basically defines the objective and the constraint. Okay. So you can read this on your own. So let's define this by Shift-Enter, running it. And now we're going to do particle swarm optimization, which we will use a library from PySwarm. And we're going to run a total of 5 times, and we record all the values we found. So the values X basically means the design that is proposed by our machine learning algorithm that you should be doing in your lab in order to achieve what you need to achieve. Okay? So let's run that. It will take a while. So now basically imagine that you have, you know, I think 200-ish particles moving on your design space and telling each other, you know, which one is the best design they've come across. Okay. Okay, so now this is done. And what we're going to do is something interesting. So we actually, the data set that we had, I have given to you that so far we've been playing around with is not the full data set. There is actually one extra data point that I deleted from the set. And that one data point actually satisfies all the sort of arbitrary looking constraints that I've given, right? And it also minimizes the objective. So this is an actual data set, so actual result of experimentation. So if our search succeeded, so our inverse design succeeded, the design should help us, you know, get close to that particular data set. So that will be a way to guide us to do this experiment. So let's compare the results that we had from this particle swarm optimization with the real data set. So here you can see this table. The first 5 rows are the suggested designs from a machine learning algorithm. So these are sort of the designs we found by doing this optimization. And the last one, color red, is the true experimental data point. Okay? And you can see that some of them are actually quite close. And this is only on a very short run. So let me show you the result on doing a longer run on more number of tries. Okay, so remember this is our task, and we do swarm optimization, and these are the results. So I compare 3 different designs. The first one is the actual unseen experiment. So this is the real thing that's supposed to happen, and we want the machine learning to help us get here without actually doing the experiment. So you can see that the design by gradient boosting regression gets fairly close. Okay, this is the closest one I've seen from 100 runs. So it gets fairly close to this design. Whereas if you have used a bad regressor, so a bad forward model, or kind of a bad, you know, virtual experimentalist, then, you know, you probably won't get very close. So these bottom row of values here are the ones found by inverse design by linear regression. So a good fitting model is useful. So as we demonstrate here, that it's useful to guide how to do experiments. Okay. So this is my last slide. So here are some resources on more data sets of this nature that you can play around with, and also some useful references. You've seen one of them on various machine learning, deep learning techniques that you can use for your regression problems and beyond. All right, so this is all I have. Thank you very much.